Okay, so in this video we'll quickly go through the chain rule of differentiation. So here I have two graphs. This is the graph of x with respect to t, and this is a graph of y versus t. So both of them have t on the x-axis. This one has x on the y-axis. So we are plotting some value x, let's say, and here on the y-axis we are plotting some value y. Now, so let's say at some point, let's say at this point, okay, this point uh, in t. So when t equals, let's say 5, or let this be any point, okay, a, let's say this point, and here also I get the same point. I take the same point, let's say this, okay, a. So both the axes are the same, right? So I can take the same point on both the axes a, let's say, okay. And in this graph at a, here, if I find the slope by making tangent, right? If I find the slope of this tangent, okay, the rate of change at this point, so that will be, so because this is y, so I'll get dy by dt. So this is a small change in y upon a small change in t. So dy by dt. So let's say the rate of change at this point, the slope at this point, which is given by dy by dt, equals, let's say, some value p. Okay, could be anything. So some value p, which is a value. Now let me take an example here. Okay, let's say that rate of change is 5 here, and in this case, at the same point a, I draw a tangent, and the slope of this tangent at the same point will be given by dx, a small change in x, divided by a small change in time, t. Okay, could be anything. And let's say at this point the slope or the rate of change at this point, the same point in this graph, is, let's say, 2. Okay, so we have two rates of changes, okay, so two slopes at two different points, but the only thing common is the same point on the same axis. Okay, now if I say, so this could be like, so this could be the position, let's say x is the position of some runner at some, okay, at some time, and y represents the position of some other runner at the, okay, but time is common for both of them. So this is the speed, okay, rate of change of his position with respect to time. This is the speed of the second runner, rate of change of his distance, his position with respect to time. Now what if I have to find the rate of change of his position with respect to his position? So the rate of change is always with respect to something, right? So here it is with respect to time. So as time changes, what is his rate of change of position? So what I have to find the rate of change of his position with respect to his with respect to the change in his position. Okay, so we are finding the relative rates of change between the two runners. Okay, so how do I find that? So here I can treat this as a fraction, right? Obviously this is a fraction. So how is this a fraction? This is actually dx. Okay, this is dx. Okay, change in x, a small change in x upon a small change in t. So after all, this is a fraction. This upon this. So dx upon dy, this is a fraction, and similarly this is also a fraction. So how do I find? So what I have to find here is rate of change of x with respect to dy. So dx by dy. Okay, so, or let's say, let me flip this. If I have to find rate of change of y with respect to x, so I'll just flip the thing, dy by dx. If I have to find this, now how do I find that? So I simply divide this fraction by this fraction. Okay, if I divide this fraction, what do I get? So I'll do it here. Okay, dx by dt, I'm taking this fraction, divide it by this fraction. Okay, I'll just use the same color. Okay, dt. Okay, and what do I get? So I'll just flip this and turn this into a multiplication symbol. This is the same thing as multiplying this with dt by dy, right? I can cancel the dt with the dt, and what I get is dx by dy. So if I divide this rate of change by this rate of change, I get dy by dx. So I just remove this intermediate step here, and okay, so I'll just write it here. Yeah, so here I go, and yeah, so if I divide this by this, I get this. So what is the value of dx by dt? So I'll put the values into the equation here. So dx by dt, the value of this is 2 here. Okay, so I do 2 division says division, divided by dt is 5. So I write 5 equals, so this is dx by dy. Now if I just solve this, what do I get? So I get dx by dy equals 2 upon 5. So you can just write that as a fraction or convert that into a decimal form, but that's not of importance. What is of importance is that I can get dx by dy, or the rate of change of different. So I can compare the rates of change of two things by simply dividing or multiplying. So it depends on how I have to cancel it, right? So I can use these as fractions to cancel them. Okay, so I can find the rates of change by doing this. Okay, so that is one thing. Now, how is this useful? Okay, so I'll just quickly. I'll just quickly rub all this. Okay, so what we learn from this thing is that we can simply use the dy by dx notation not just as a notation but also as a fraction. Okay, so now let us take a real a better example. Let's say somebody asks you to differentiate this. Let's say he asks you to differentiate um, x plus 5, okay, whole square. One method is to actually, okay, so use the formula of a plus b whole square. So you can write x square plus 25 b square plus 2 into x into 5, okay, and then distribute your derivative, okay, and then find the derivative of the first term, second term, third term, add them up. That is one way, but there's a shorter way using the chain rule, okay, using the concept that we just used right now. So okay, so I differentiate this dy by differentiate with respect to x, okay. So what do I get is I get d of, so dy, right, and y equals this. So instead of writing y, I write x plus 5 whole square. So d of this whole thing, a small change is this whole thing, divided by dx. Okay. Now I don't know how to solve it directly. So what do I do is I do a small trick. I actually what do I do is I actually multiply both sides here. Okay, so multiply both up above the fraction and below the fraction with dx plus 5 upon, okay, so yeah, so I'll just multiply the whole thing with into dx plus 5. So this whole fraction just is just equal to 1, right? So I can multiply this with this, okay. So why am I doing this? Wait, I'll just show you in a moment. So this whole dy by dx equals, so I can write this as dx plus 5 whole square. Now I can switch these two, okay, wait, into this, into d of x plus 5 whole upon dx into dx plus 5. So this is just a mathematical trick, okay. Obviously this has some physical significance, just as I showed you before, but yeah, this is after all a mathematical trick. So now the order of these two doesn't matter, right? So I can just switch them. So I'll switch them. I'll write dx after dx plus 5, okay. So I'll write dx plus 5 here and into dx, okay. Now I'll just write these two as separate fractions, and now you can probably see why I did this small trick here. So now what I get is dx plus 5 into dx plus 5 upon dx. Now this part is easy to solve, right? Dx plus 5 upon dx plus 5 upon dx. So I can just distribute the derivative, okay. So I'll solve that later, wait, okay. Now let's come to this point, this part. Here I have d of something square upon d of something square. So we can, obviously it's very easy, but I can also do an additional step here. Let x plus 5 be equal to, let's say, a. Now what happens is the whole thing becomes d of x plus 5. So I can just write d of, instead of writing x plus 5, I can write dA whole square upon dA, okay. So I have just substituted the variable here from here, okay. So this is done. I suggest you to write this variable. Why? Because this will reduce the complications, and it will avoid, just to avoid confusion here, you should actually let this whole thing be equal to some variable a and then put in. So now we have simplified the whole thing, right? And here I just distribute the dx. So this simplifies dx by dx plus, okay, I'll just into brackets, and d of 5 upon dx. So this is a constant. Rate of change of a constant is simply 0. So this simply gets 0. So I'll just remove it. It gets vanished. Okay. And dx by dx is 1. Okay. So I just that cancel out and becomes 1. So something into 1 is just the same thing. So we don't even need to write this. In that vanishes. What is dA square by dA? That is simply equal to. So what is this? It's like finding the derivative of a square, right? X square, a square, same thing, right? So dA square by dA is simply 2a. And now I can substitute back again to get my original variable. So 2 into x plus 5, which is simply equal to 2x plus 10. And that is the that is a shorter way of finding the whole thing. Obviously this looks longer, but when you do it, it's easier. And this is a simpler example. If for example somebody asks you to find the derivative of sine x square, so there you find first, so there you let your x square be something. So I'll just quickly do it. Actually, let's remove all this. So I want to keep this video short. Okay, this is a very simple topic. So you use it where your derivative looks very complicated and you can't find it directly, or you just can't distribute a derivative. Okay, so let's say, taking another example, sine of x square. We can't do anything with this directly, right? But we can actually let the whole complicated thing. Okay, so here this function looks like a two-step function, right? First we have to square the number, then take the sine of it, and then you get y. So let the second part, half of that, okay, the half of that function be let x square equals a. So I'm just going very mechanically. Okay, obviously there's a lot to it, but I want to keep this video short for now. Sine x square, and x square is a, so I write sine a. And now I can find the derivative of this. So dy by dx, oh, not okay. So dy by dx equals d of sine a over dx. Now I simply do it again into dx upon dx. Sorry, into dA upon dA. Now I can simply switch these two, right? I can switch their position, it doesn't matter. So I write it as dA here and get the dx here. Now I can find the derivative of this. If you know that, simply comes out to be cos A. Okay, dy by dx into, now I substitute back the x square here, so I get dx square by dx. And now this is pretty simple for you to solve. Dy by dx equals, so cos A, I can write that as cos x square, right? Substituting back into my original variable x square, into dx square by dx will be simply 2x, and that is your derivative. So that is how you find your derivative. And one simple way of one simple way of finding when you want to use your chain rule. So this method is called the chain rule. Okay, so the simple way of knowing when to use this chain rule is, so whenever you have a function which has steps, right? Like the previous example has had steps. Okay, so just imagine, how do you process the number? So first you square. So if you take your number, if x equals 5, so first you square that number. 5 square 25. Okay, and then you find the sign of that number, and then you get your y. So here you are doing it in steps, right? And in such situations you need to use chain rule to find the derivative. So that's it for this video, and I hope you've got the chain rule. Bye.